Well, hello there, everyone. I am back on YouTube with a new electrical engineering project in the context of a microwave electronics course that I took this semester. So, throughout this video, I will be presenting you my design and I will try to explain the rationale behind the choices I made and how they turned out in the end. Did they work? Did they not work? Could we have done them in a better way, and so on. So let's start, shall we? I mean, here I want to show you the basic final schematic of the design first. Here you can see a test setup. You can see the most general test setup for our design. Here we have the biasing voltages. Actually, sorry, and here we have the supply voltage. Actually, let me go through our process, our technology first. So as you can see here, we are using a gallium nitride technology provided by the CREE foundry, one of the most established gallium nitride foundries, and one of the foundries whose process design kits are very detailed, so we can work with their nonlinear models extensively and simulate our designs extensively. So that's an advantage for us. So the basics you need to know is uh, these devices are depletion mode devices, and our transistors operate in from 0 to -3 volts. So because they are depletion mode, the -3 volts is actually the threshold voltage, and 0 is the basically maximum gate voltage you can give them before they start acting weird. So above 0 voltage, they actually start to draw current from the gate terminal, and they become like they don't act like we want them to act. So we want them to act like depletion mode MOSFET transistors, and they do act like that in this range. So that's basics covered, and we are operating at a supply voltage of 28 volts. This is specified by, again, the foundry. So these parameters are specified by the foundry. Okay. So let me go over the design really quickly. Sorry. So if I enter the design here, you can see it looks kind of intimidating and complicated first, but it is actually quite simple. It consists of like quite simple main components. Actually, here I have a more basic representation for you. So the differences from the design you see before, I replaced all the real components whose models are provided by CREE with ideal components whose ideal models are already present by default in ADS. So we are using ADS as the simulator of our choice. This is also mostly determined by the PDK availability. So sorry, let me go through the design here. So our design goals for this project was to design a high linearity low noise amplifier. So what does that mean? That basically means we are going to have a low noise figure. So noise figure was a big priority for us in this design. And the second rule of our design is to have actually maximum gain that we can achieve. We were asked to design a two-stage amplifier for that purpose, and the third one is actually the linearity of the design. So sorry, I'm not going to use this page here. So the third parameter is linearity of the design, right? And linearity here is measured by the IP3. So why do you need those three characteristics in a device? There could be a couple of reasons, but as far as I can tell, the main reason is these amplifiers are needed. So LNAs are always the start stage of a receiver circuit, because we want them to amplify our signal without distorting it much, And after the amplification there, we do not have to worry about distortion much because the signals are amplified. The noise added by the other amplifiers in the system will not be a problem, or other passive components. Sometimes mixers also add noise. So that's basically the properties of an LNA. That's classical. But why the two stages and the noise figure? Well, firstly, we need a high gain amplifier. That's obvious because if you don't have a high gain amplifier, actually the noise effects of the other stages, the stages coming after the LNA, will be bigger because their effects are divided by the the gain of the first stage always. And by the way, we need high linearity as well. As far as I understand, in certain military applications, they actually need LNAs with high linearity because adversaries, let's say, OP4, or let's call them OP4. OP4 is trying to sabotage your communication systems by sending these very high power signals that is going to saturate your LNA. If it is a low IP3 LNA, it's going to saturate it and make your system basically break down essentially. So these are the rationale behind the characterizations. Other than that, we had a frequency range. I actually chose, everybody in the class chose a different frequency range. I actually chose the highest for this process. So the highest recommended frequency for this process is 8 GHz, and I am here working between 722 GHz and 798 GHz with a center frequency of 7.6 GHz. So there is that. Other than that, let me go through the design choices here. Let me go through the design choices we made here. So the first one is, first here you can see the input matching stage, right? This is pretty standard to use this kind of arrangement. We are using T-lines because they will be easier to implement when we are doing the layout, and well, they will give us better simulations, better results in EM simulations, basically. Then we have got our biasing actually, which is something I wanted to talk about extensively because it is one of the important design choices. But let's talk about it in the very last section. Because, well, it's an extensive discussion, let's say. Then we've got our stability circuit. Actually, here for the input matching, the required the return loss, input return loss must be below 8 decibels throughout the band, our band. So between 722 and 798 GHz. I'm sorry, sorry for that. Then we get our stability network here, consistent of these. Well, I have choose to use the stability network at the output side because obviously that's better for the low noise part of the design. Other than that, as you can see, it's integrated to the supply side, which means we need to use less transmission lines, less components while actually implementing the design. Then here we have a matching between these two stages. Then we go to the second stage. Again, we have another transistor, another amplifier with again the stability network at the output side, and then we have output matching network, and actually our output return loss criterion was stricter than our input return loss criterion. It was the output return loss should be bigger than 15 decibel throughout the band. Excuse me if I said smaller than 8 decibel at the beginning. It should be bigger. The return loss should be bigger, and the reflection should be smaller than 8 decibels for our circuit at the input, and it should be return loss should be bigger and reflection should be smaller than 15 decibels. Actually minus 15, but whatever. So you get my point here. So one thing I want to touch actually, why is output return loss defined more strictly for this design compared to input return loss? Well, when you are using an amplifier like this in a receiver circuit, let's say, you are probably going to cascade it with more amplifiers. So if you have bad output matching, the amplifiers you add after that will cause a problem, right? But for the input, this is usually the first stage of an sorry. This is usually the first stage of a receiver, so the input stage won't cause that much of a problem for us here. And another thing is, of course, for the noise optimality, we are sacrificing from the input return loss by matching the not matching, but transforming the input transforming the source impedance to our optimal source impedance for noise figure, right? So there is that. So let me talk about the biasing. Actually, you can see here I talked about our range. Our range is between 0 and -3. So we are actually biased as a class A amplifier. I will answer the rationale behind that. And actually we have a comparatively large transistor for both of the stages. So both 450 micrometers, as you can see here. There are all of these rationales between these, and I am going to explain them in this simulation that I am opening right now. Sorry for the delay here. Yes. Okay. Let me open it. I think here it is. So as you can see, we have here got a very simple test circuit for our transistor. And what are we going to check here? We are going to check the maximum gain, which doesn't depend on any input or output matching circuit, because it is independent of that. It is defined independently of that. It is defined assuming that the input and the output is perfectly matched. And let's look at our minimum noise figure, which is again defined such that the source impedance is at the optimal impedance for noise. So let's check that out. I'm running simulation here, and yeah. So these are the graphs, and I'm going to open tuning in ADS actually, which is a nice feature, and I'm going to tune the width of our transistor and the DC bias voltage. Let's see. So here is my tuning circuit, as you can see. Tuning guide, let's say, sorry. Okay. So let's play with the width for a moment. If we decrease the width, actually, as you can see, the noise figure decreased. It was something like 2-3 at our width, but here it is 2, which is quite good actually. Quite. So remember, when you are seeing these noise figures, we are at room temperature. We are testing it at room temperature. In the end, I plan to show you the test for my circuit in below 0 temperatures. But here we are at room temperatures, so these noise figures are not actually that bad. So when people think about low noise amplifier noise figure, like they think something like below 1 decibel specifically. So 0.8 decibel, 0.6 decibel is really good. But you can't achieve that in room temperature. So judge this accordingly. And this is actually the process, the minimum of the process itself. So I am not doing anything here. I am not designing an amplifier around it. So there is also nothing I can do about it. Anyway. So by actually choosing the width larger, we are actually sacrificing from minimum noise. But let's see what are we getting. As you can see, I drawn the maximum gain circles and maximum available gain circles and minimum noise circles for the source impedance. as you can see, as we decrease the width, they are moving further and further apart from each other. So you just saw that. But if we increase the width, let's see that, the noise figure increase, but these two circles come closer and closer. So remember, we also have a input return loss criterion, which we must also satisfy for a successful design, and this makes it possible actually. This closeness of the circles makes it easier to design an amplifier that is satisfactory for both the noise and input matching, basically. Another advantage of using bigger transistors is actually they are quite helpful for the linearity, for the IP3 figure, because bigger transistor, more linear transistor, it can handle more power without getting saturated. Well, actually, gallium nitride transistors already can handle quite a bit of power without it's smaller widths, like 100 micrometers and such, that they can still handle good they can still result in good IP3 measurements, but still our method makes it better. So I will show the results for that, but a little teaser, we are getting more than like 45 actually output IP3 and more than 20 input IP3, which is really good. And 40 and 20 are in dBm scale, for those who are curious. So let's actually see the impact of the biasing voltage. So as we decrease the biasing voltage, as you can see, gain increases a little bit, but we are already using two stages, so we don't have to optimize for the gain at this stage. But the noise figure really shoots up, so we don't want that. We don't want to work at a process where the minimum noise figure is actually 3. That is inconceivable. Sorry. So we are not doing that. So that is the rationale behind it, basically. Let me correct these figures and go back to my design for the moment. Alright. So now I am going to show you the complete schematic. This was the schematic with the ideal components. Now I plan to show you the complete schematic with actual CREE components. Let's go. So here is our test bench again. As you can see, well, it actually doesn't have to get this complicated, but we also wanted to simulate the bands and other geometric figures in the schematic, because these bands actually have electrical models for the CREE library. So we actually created a schematic design very consistent with the layout. It was updating using the layout. We first did the layout and then updated schematic to match it. So again, here you can see the basic input matching network, the DC block capacitor here, and then the biasing here, very simple biasing, a DC feed here, an RF choke inductor. Then we have the stability network here. As you can see, in the stability network, because we were using small inductances to give us higher gain at larger frequencies, we can actually replace inductances with completed transmission lines who actually act as like series low pass filters. So they are doing the inductor's job there. Again, moving forward, here is our matching circuit between two transistors, and then if you go forward, again you see the second stage, the biasing of the second stage here, then we got the stability network of the second stage, and finally the output biasing. Right. Again, I want to highlight that we choose to put the stabilities at the output so that they don't affect the noise figure as much. Because if you put a like resistance in the input stage, yeah, you are not going to have that good of a noise figure because yeah, resistors create a lot of noise, especially at room temperatures. So that's the design. Let me simulate the design to see its S parameters here. So the simulation finished, I think, successfully, and here are our results. So again, with these two stages, you can see here is our max gain, which is at 21.2 at the middle of our band. Sorry, this should be 76 actually. So it is 21.2, 21.3 at the middle of our band here. And you can see actually here the minimum noise figure. So again, so there is a difference in the minimum noise figure here, and I want to explain that. So you saw the minimum noise figure for the transistor, right? Then we are adding on top of it the stability network, which affects it, which makes which degrades noise figure because stability networks are resistive, right? They are not lossless. Then on top of that, we are actually not directly matching. As you can see, we didn't directly match for the optimal noise here. We are making a sacrifice between the input matching and the noise. So then we are degrading this figure here even more to get our actual figure, which you will see in a moment. Again, this figure is not the maximum gain directly for the transistor. It is for the amplifier with the stability network in place. So these figures are actually already degraded a bit. So don't get confused by that. So here is our stability factor. As you can see, it is unconditionally stable, of course, but it is one interesting thing. It is also bigger, quite much bigger than 1, right? So you could ask here that, well, like why sacrifice some more from the stability factor to increase gain, essentially? Well, I will show you the gain in a moment, but the gain actually is pretty close. Sorry, I will show you the gain in a moment, but our gain is quite satisfactory already, and we actually added another gain specification, which is the gain variation in our band should be smaller than 1 decibels. So you actually find the gain here at the middle of the band. Sorry, so there is not that many points, but as you can see, you find the gain at the middle of the band, and you look at the variation between the two extremes. So that should be actually, this part of the variation should be less than 0.5 decibels, and this part should be also less than 0.5 decibels. So there is also that specification which makes you sacrifice somewhat from achieving optimal gain. And the other thing is actually, when we do the EM simulations, the stability factors drop considerably. So there is that. So we can't actually sacrifice from the stability factor in this stage of the schematic design. Anyways, as you can see, these graphs have somewhat low resolution, but that is by design as well, because we are doing the EM simulations for the same figures. I didn't want to use too much points, and so the simulation runs at an acceptable time limit. The EM simulation runs at an acceptable time limit. So there is that. So let's go over our characteristics here. Here you can see the input reflection, so basically the negative of the input return loss. As you can see, our standard was that input reflection must be smaller than minus 10 decibels, or input return loss larger than plus 10 decibels. Sorry. As you can see, this perfectly matches the design, and actually, as you can see here, This is more or less matched to the middle of our band. So we are getting actually a nice notch. Well, not really. Well, yeah, we are not getting a nice notch at 7.6. So that is nice. Again, you can see the gain here, 20 decibels of gain. It is pretty good. For our process, actually, you saw the gain for the one stage we chose without any stability network was around 14. So that makes, if you somehow magically match two stages without adding any stability to them throughout a band, you are going to get 28 decibels. And here we have an unconditional stable circuit who is actually optimized for noise, not for the gain. So optimizing for the noise is another gain sacrifice we are making here. So with those sacrifices in mind, it is actually pretty good that we are getting 21 decibels gain, and well, it is actually quite stable throughout the band, it is not a small band, right? It is nearly 1 giga or so, right? It's a pretty respectable band for an undergraduate designer. Anyways, then we have here our output matching network. Again, our standard was that the output return loss must be larger than 15 decibel, output reflection must be smaller than minus 15 decibel, the same thing there. As you can see here, the notch is not actually at the middle of the band here. So you might ask, why not, Berk? Why not put the notch at the middle of the network? Actually, it is due to like EM simulation results. At the initial schematic design, I put the notch there, but in the EM simulations, the notch moves toward here, and actually matching at lower frequencies, output matching at lower frequencies, end up being really, really well matched. But the higher frequencies suffer. So that is a design choice by us. So again here we have the noise figure. As you can see, so here we saw that our minimum noise figure at 25 degrees room temperature, right, was around 2.3 decibels for a single transistor, that is without any stability, any real components. So that is the absolute best you can achieve basically if you are designing a circuit and you acquire somehow a magical power to match and stabilize transistors. Well, I don't have that power, unfortunately. So we are making a couple of sacrifices from the noise figure here. The first is adding this stability and unconditional stability. That is a huge sacrifice from the noise figure. The second is lossy component. So actually in this form of the design, when I simulate this form, I am actually getting a 2.7 decibels noise figure. So replacing these perfect ideal transmission line models and basically ideal capacitors, ideal inductors here and there, affects the noise figure by, in the schematic, by 0.2 decibels, and actually in the EM simulations the noise figure come around 3.1 decibels. So those are the sacrifices we are making, and again we cannot fully optimize for the noise as well because we have a input return loss requirement. So again we are making a sacrifice from the noise there. So I just wanted you to know that. After this, actually I want to show my layout to you. So here is actually the layout for the design I just showed you. So let me walk you through it actually. Actually one simple thing we did, one comparison you can make here. Let me show you that. is we, oh sorry, I talked about it. We replaced the inductors here at the stability networks with very nice transmission lines. So, oh sorry, another sacrifice we are making for the simplicity, for the sake of simplicity, is we are using constant width transmission lines. That makes the layout design process easier and faster, which is a good thing because I had very limited time doing these designs. Because even though I am graduating this semester, I have like 4 projects to complete for the same week, which is the final week of the school, and which is the border week between school and final. So sorry for the rant there. Again, we are using constant with transmission lines for ease of design. We can just add them, no problem. Then one thing we didn't do, if you want to make the design smaller, so we have one branch, only one transmission line branch here, as you can see. We could add 2 branching transmission lines, which would have made the overall length of the transmission line smaller. Another thing we could have done is, because these transmission lines are basically capacitances, shunt capacitances of open circuit, they have an electrical length less than 90 degrees, all of them, as you can see here. The electrical length is very much less than 90 degrees for all of them. So they are capacitive lines, they are effectively shunt capacitances. So we could have used actually larger sized lines to make the effective length shorter for the same matching, but we also didn't do that for the sake of simplicity. Anyways, let me show you the design here. As you can see, we start with the RF probe. We curved the lines quite a bit to make our design smaller. We have essentially the input matching here. Here is the input DC block. As per the requirements of the process, we are taking one input of the capacitors from metal 1 layer and the second input from the metal 2 layer using the Capcom device. Then we have input, we have the biasing of the first stage. Then we have here both the stability and the supply of the first stage. Then we have a DC block again. Sorry. Then we have the matching in between these 2 circuits. Then we go on, and again we have the biasing of the second stage here. These are ground pads for our design. These were the biasing pads, and this is the supply pad. This is also a supply pad. This is the second biasing pad. And these are RF probe pads, actually. Then we have the second stage and basically the output matching of the second stage and supply of the second stage here. The entire area of our design takes, let me measure it, as far as I remember, it takes 4 millimeter, right? Yeah, 4 millimeters length, let's say, and 7 millimeters high. So it is a 4 to 7 design. The ratio is a bit odd, I know. The overall area is 28 millimeters squared. I know some chips are smaller. Usually chips are around 3 to 3, like 3 to 5. I know that. This is a little bit larger. But I have quite a short amount of time to go through EM simulations. I didn't want to deal with any, weird couplings between lines, solving that. So that's why I went with the larger route with a considerable amount of empty states. But it is also not that large, right? It is still like an understandable design, I believe. Anyways, so here is the design, as you can see. And right now I'm going to take you through the EM simulations of it. I have already extracted, as you can see here, EM co-simulation model. I will in a moment import it to my simulation setup, but first let me show you actually the IP3 of the ideal design. So let me close off the S parameter simulations here and open up the IP3. Hopefully it will run in a reasonable time. Did I forget to do something? I don't think so. Oh no, it's still running. Alright. Here it is. So as you can see here, we are getting around 45 decibels of IP3. So that is very, very nice actually. That is something commendable. But this isn't the output IP3 measurement. So this is the place where the extrapolation of the third degree parasitics and the fundamental signal power meet for the output power. So this means when the power of our fundamental input signal, the amplified power, is 45 dBm at the output, the third degree parasitics extrapolated. So actually saturation happens way before that, but the extrapolated power of both the fundamental signal and the output parasitics will be at 45 dBm, which means the input IP3 is actually around 25 dBm because we have a gain of 21. So there is that for you. Right now, let me actually let me actually change the simulation back and simulate it again and compare our schematic simulations with the extracted EM model. One nuance here is that we can't actually extract. So here is our parameters for this. Sorry, I forgot to open something. Sorry for that. We can't actually simulate the transistors in the EM layout because we don't have the substrate models and such of the EM of the actual gallium nitride transistors. So we are still using the nonlinear models provided by CREE rather than an EM simulation, of course. Any other component we can simulate, and we are simulating it in the EM simulation. So let me run this again. So here you can see again the circuit things I already shown, circuit simulations. Here I'll open the history and go ahead and change this model because I have already run this simulation before. It won't take long, it won't take a long time, I hope. So I will run it for the EM this time. I changed the model to cosim, right? Here, as you can see, actually, the differences from the EM is actually quite stark. We don't actually get much difference with the maximum and minimum figures. Actually, the minimum noise figure is quite amplified, it's 3.1. And the gain is already, well, attenuated. As you can see, even the maximum gain is attenuated with our stability network in place. Well, but yeah, with our EM the EM version of our stability network in place. And actually, we are also getting quite a bit worse stability. So we are getting around 11, we were getting around 11, we are now getting around 6. So that's a significant drop there. Again, if you go over here, as you can see, the input matching moves to the right, so it favors higher frequencies, and the output matching moves to the left, and all in all, the gain moves down, of course. Starting with the input matching again, we are still basically satisfying the standards. We are below 8, minus 8 throughout the band, and that's great, that's good. Then moving on to the output matching. As you can see here, the thing I said happened. It favors lower frequencies over higher frequencies. But as you can see here, we are still below minus 15 here, because we adjusted our design to fit that criterion. Our EM design as well, we adjusted that. Oh, actually, so let me talk over this and we'll visit the layout once more. Alright. In our gain, well, our gain is naturally dropped quite a bit. It was 21, it dropped to 19.5. So around 2, we are seeing an around 2 decibel dropped. But again, 20 decibels are still commendable, because we are actually sacrificing a lot of gain to get other things, other meaningful things, to get, you know, low noise figure, like better unconditional stability and so on. It is important to keep your sacrifices in mind while designing circuits. Anyways, as you can see, the gain variation though is still low. We are getting basically our criterion was 1 decibel overall gain variation. We are getting, I think, less than 0.5 decibel overall. Other than that, if you check the noise figure here, as you can see, it is increased quite a little bit. Like, it is increased, I think, 0.2 decibels. But that is quite normal when you like move your design from conceptual to reality, right? Again, as you can see, 3 decibels are, well, I think it is commendable still at 25 degrees. Actually, I plan on like showing you, let's close the history, like make the history off here, so we are only seeing the EMs here. And let's look at our design at like minus 10 degrees or minus 20 degrees, so at like frozen temperatures, right? Yes. So I will add an option for the experimental simulation and make the temperature minus 10. So you may say, oh, Berk, why are you making the temperature minus 10? Oh, actually, we are not seeing an decrease, commendable decrease here. Sorry, maybe it is because the EM model extraction. Let me go to schematic first, then run it again. I don't know, is it because of model parameters, I guess? Are there temperature characteristics that... Yeah, there's a temperature parameter at the transistors. Anyway, you could ask yourself that, you know, Berk, why simulate at, you know, minus 10 degrees? Are you going to use your amplifier in a fridge? Well, yes, actually, low noise amplifiers are running fridge-like devices, basically, that keep them cold and thus low noise. So that isn't outside of imagination. Anyways, let's going back to the layout here. I want to show you actually the DRC. Even working with the quite complicated CREE design rules, as you can see here, we are not getting any DRC errors. So that is commendable and nice. And it also means we can send this to manufacturing and test it. But unfortunately, we didn't have time for it. But hopefully, I hope to someday make circuits like this and actually test it. Anyways, let me show you the comparison of the IP3 from the comparison of the circuit model and the EM model in terms of IP3. So let me close off the experimental simulations here. So it was weird actually. decreasing the temperature in the app options and still seeing the same noise figure. I will probably address that in the description of the video if I find an error in my simulation methods. I'm going to ask Arent about that, so that was weird to me as well. Are we still at circuit? So let's simulate the circuit first again for the IP3, then we will simulate the EM model, then we will see the differences. Alright? So it takes a quite while actually doing, power steps here, because I am using quite a bit of power steps, to be honest. As you can see, we are getting 45, nice and easy. Then we are moving on to the EM co-simulation model here. Okay. Sorry. Let's keep the history open first. Let's simulate. So as you can see, we are getting more or less the same thing. So our figure didn't dictate, but keep in mind that we don't have actually physical simulation models for the we don't have the EM models of the substrate interactions of the transistors. We are still using the nonlinear models, circuit nonlinear models of the CREE, because the CREE foundry doesn't provide that sort of models for EM models for transistors. So keep that in mind while looking at this figure. Anyway, I think that's all. As I said, if I find any interesting things about the noise figure and the operating temperatures, I will share them in the description. So make sure to check this out, and I hope to see you again with designs like this in the future. Bye bye. Again, I say bye bye, but I can't close the recording. Bye bye.